Yeah, it's my pleasure to be here. Right? Everyone makes this joke, I guess. Yeah, so I'm from ETH. Actually, this week we decided to do a spontaneous vacation because there's a school break. So we're actually in the Italian part of Switzerland at the moment. I say this because if there's any trouble with the connection, just let me know. Also, if you want to interrupt the talk, I don't mind. Right? So yeah, today I want to tell you about some old and new work, actually. So you see here, the title is Belief Propagation Decoding by Passing Quantum Messages. And let's see if I can do this right. So there's two archive sort of numbers here, and one is a bit older. That's where this work actually started. And then lately I've picked it up again with a PhD student, Christophe Piveteau, who's joined us at ETH, and we're making some big strides in this direction that I'll tell you about today, or I'll tell you mostly about the older work and how we understand it a lot better, and then how we want to progress with that. So the general setting, and maybe this is the most important thing I wanted to get across in this talk, is the following. So, okay, so we're thinking about, we're in the setting of graphical models in probabilistic modeling, something that you guys are probably more familiar with than I am. And so these are very useful tools in dealing with, like, describing a lot of random variables with very structured dependency relations. And it's useful in machine learning and error correcting codes and satisfiability problems and optimization problems and physics problems also. And so it's a huge topic. Here's just a picture of some particular graphical model, I'll come to in a minute. And the main thing I want to get across in this talk is actually that it seems like there's a lot of stuff that we can think about in the quantum direction here. And because it's such a vast topic in the classical world. And so I wonder what we can do in the quantum case. And the one thing that's really nice about it classically is nicely encapsulated in this quote here I recently came across. It's just part of a review topic or view on this topic by Michael I. Jordan, the Michael Jordan of statistical modeling. And he notes that what's most distinctive about the graphical model approach is its naturalness, describing, formulating the problem, basically, formulating probabilistic models of complex phenomena, applied fields, and while maintaining control over the computational cost associated with doing stuff with these models. And so that's, of course, directly your guys' topic. Yeah, these two things together are really fascinating, I think, about this. And so, of course, the question is, can we just have quantum versions of this, right? Let's put a cat around this graphical model. Now, more specifically in this talk, we can segue into the topic here a little bit with a little quote that actually I heard Ben Schumacher in a talk long ago, too long, so I won't reveal how long, saying that to do research in quantum information theory, you just pick your favorite text on classical information theory, open to a certain chapter, and try to translate it into quantum language. I mean, this is not really how we do it anymore, but back then this was very much how we did it, I think. And so what I want to focus on here is a specific processing task with graphical models, which is decoding of error correcting codes. And actually that is the topic of this book by Richardson and Urbanke called Modern Coding Theory, very famous book. And in fact, I just opened to a certain page and stole the graphical model of the error correcting code from, well, I guess it's page 76. Doesn't really matter. The book is mainly about how you do belief propagation decoding of classical codes and why it works, okay? And so the specific, if we go back to that picture of the cat around the graphical model, the specific question I want to address is, can we do quantum belief propagation decoding? And what I want to get across is the main thing, as I said, I wanted to get across is that maybe this particular topic is a way into this bigger area of quantum graphical models. I actually don't have any great ideas about how to jump into that area in a quantum sense, except to pick this specific topic that I know a bit more about. But we will see that we do get a very quantum, we get a quantum algorithm out of it, and it is very analogous to the classical belief propagation algorithms. And so I think it's interesting, maybe even if you're not interested in error correcting codes and so on, it's maybe interesting as a way into this topic, a very specific instance of some kind of quantized, so to speak, graphical model and the algorithm that goes with information processing in that setting. Okay, so with that sort of motivation out of the way, let me show you the outline of the talk, what I want to tell you about specifically today, and it has several parts. So first I give just a quick background in factor graphs and belief propagation. The particular picture I showed before was a factor graph. I'll explain what that is. In fact, it has an interpretation, or one of the formulations is very close to things that we work with in quantum information theory all the time. So it's very nice. And then the main part perhaps is to describe the quantum version, which we call BPQM. Actually, this came up in a subsequent paper on this topic, this acronym for it, just belief propagation quantum mechanics, I guess. And this is going to do a specific chore for us in the error correcting setting to estimate single bits of the code word, which I'll explain in a minute. And it does so by passing quantum messages if you want. And then we'll see about how to use this to decode an entire, the whole error correcting code. And finally, to show that it's not just a curiosity, there are some applications of this, and you can actually get very efficient decoders for high rate codes, in fact, that can achieve capacity even. And then finally, all of that will lead to many, many open questions. Okay. So yeah, let's move on to, well, doesn't really want to go. Okay, yes. So it just highlights the factor graphs and belief propagation section. So I'll return to this outline to break up the talk into different parts so you can get back on board if something goes wrong. Okay, so a little bit more about graphical models and then this belief propagation algorithm. If you're all completely familiar with this, just tell me to go faster. But here's a picture of the different graphical models. Remember, graphical models, we were trying to describe random variables that have structured dependency relations. And so there's actually a few different formalisms for doing that. This picture, which is out of a nice review article by Andy Lurliger, who's a professor at ETH, just shows some of the different ones. You might be familiar with one of them, you might be familiar with a different one. And so, just to go through the four of them, here's a Bayesian network, here's a Markov network or Markov random field. We have these random variables, X, Y, Z, U, and W. And this is sort of, I think the Bayesian network is maybe the nicest one to see the dependency because you just write it with the arrows. And then in the error correcting community, there's a version of this called factor graph, and this is the kind of usual version of that. And this is the so-called Forney style factor graph. Forney is a sort of famous researcher in error correction. And what these pictures are trying to do is to describe this, like the factorization property of a probability distribution. I think this is for me, the most immediate way to think about it. So we have some probability distribution over the random variables, and it has a specific form, which you see here. And this is very much encapsulated in the diagram, right, or in the graph. Okay, so it's just trying to represent this factorization. Okay, so here we'll focus on the Forney style factor graph. In fact, they are just what we would call tensor networks, I think. And so I illustrated it with a probability distribution, but in general, they just describe the factorization of any function if you want. And the rules are that there's one vertex or node, I'll probably just call it node, per factor. And the edges represent the random variables or half edges. And there's one edge per variable. And if you need to reuse a random variable, you just duplicate it with this equality node. So you can see here, I've just copied the picture over from the previous page. So the random variable x here, I mean, it's the same. It's going to be the same as the variable associated to this edge and to this edge, because this node here is equality. It just means that all of the legs are equal. And then we just connect nodes, here there's the boxes, to the edges when, so node f is connected to edge x if the random variable x appears in f, the function. And so here, so for each of the, each node is associated with this, with the factor here. So like this is the node that goes with factor pu. This is the pw factor, and so on. I mean, this way of writing it out, I did just to be completely clear. So we have nice names for the nodes, or for the functions that go with each node, and then we have also the actual values that we're going to sum over. So in fact, this picture here, although in the previous slide, these were just, so I claimed that, let's go back here, it was trying to describe this general probability distribution that isn't quite true for the Forney style factor graph. It's actually describing just the y and z part, because these are the half edges. Okay, and so it's basically just tensor network. And so here we have random variables that go with these edges. And if we want the probability distribution of y and z, then we just need to contract this thing. And the contraction pattern is exactly the factorization of the probability distribution. If you want the probability, if you want the probability of y and z and u, you can just stick in an equality node here with a half edge sticking out of it, and then you'll have. So yeah, in that sense, you don't have to be too pedantic about what the free edges are, because you can always create them with these equality nodes. Of course, this is all very classical, right? You can just copy things.
Joe, can I just ask?
Yeah, please.
So the fact that some of these things correspond to conditional distributions in a certain direction that's not visible in the graph. The graph
Correct.
just describes any contraction and that sort of extra information that might be useful or not.
Right. So
okay.
The interpretation of it as a conditional distribution and so on, this depends on the normalization, and that you can't see from the graph. And there's no, I mean, you might write arrows on these things, but I think the problem when you do that is you quickly run into cases where it just doesn't make sense to do the arrows anymore. You might approximate something or whatever, and then you don't have the same normalization that you had before. And so it's best to just not bother with that, I think. Also,
Thanks.
From the graph point of view, I like the fact that it's just a graph. I mean, you have half edges. It doesn't matter how it's oriented on the page and all these sorts of other things that sometimes happen. I mean, if you like those sorts of diagrams, great. I just happen not to. So yeah, but you're right that you can't see that in there. Okay, so this one, the claim is it would describe this probability distribution, and the way you would have to enforce that is you might say, well, all the factors are positive functions, and if you sum over all of the free edges, you would just get one. Then you would have, of course, you could just renormalize it. So the positivity is the main part. Okay, but so for us, we only care about describing probability distributions. We'll just take the nodes to be positive, but in general, you could do whatever you want, I guess. All right, good. So now one of the workhorse algorithms in this domain is belief propagation, and it's a way to marginalize basically the probability distribution by so-called message passing, which for us is basically just going to amount to contraction. Okay, so here's a different example, and we'll see this one over and over actually. So here we have some function, which is just the product of two factors, function on 4 variables. They're lined up here with free edges. And yeah, so we have the function f takes in x1 and x2. x2 goes along this edge because of the equality node. Okay, so this one represents very nicely this factorization. And if we wanted to compute, say, the probability just of x2, then what we can do is in this sort of error correction language and Forney style factor graphs, you would just terminate the edges with these half edges with also with an equality node, even though now it only has one edge, but it just means sum over that variable, right? So this whole thing here, this part of the graph is just going to take f and contract, sum over x1 on this part. And so let's see, what's the next? Yeah. So when we want to compute this value, we can just contract this part of the graph together and then feed that information into this box. Maybe I should just draw this. We can contract this part together and feed it in here. And contract this part, feed it in here. And that's kind of the messages. The messages that are going to the equality node in the middle are just the contracted tensors, or the, yeah, basically. And so then there's, of course, going to be a further contraction at this node, and that will just give you x, the probability of x2. So for certain different applications, you might be able to simplify things a bit. So for instance, if the edges can only take binary, like only take 2 values, and everything is normalized in probability distribution, then maybe you just get away with sending only 1 real number as the message. But in general, it will just be, you just contract this into some new tensor, and that's the message essentially. You just need to combine those things at this node. So that gives you a sort of algorithm for how to compute px2. Okay. Good, so the messages, as it's written here, the messages are contracted tensors, and this is very nice and easy and works, you know, basically for tree factor graphs. So it's going to be an exact method of doing this. In fact, or let's say, I guess easy is the right word. So for us right now, it doesn't make sense to talk about it on any other, sorry, we could contract any network we want. The contraction is going to be sort of straightforward or easy on a tree. That's sort of clear, right? Just work your way along from the leaves to the root. If you want to do more complicated graphs, you can, there's nothing wrong, you just contract, but then the messages will start getting very big because you just have lots of, I mean, the bond dimension is big, essentially, right? To use the tensor network language. Okay. So maybe, okay, one more point I should say about this. In the so you can define an algorithm. Here's what happens in the error correction world. Even if the graph isn't a tree, you can define sort of these rules locally on the graph, and then run the algorithm anyway. And then in that sense, okay, we won't actually do this in this talk, so I don't necessarily try to convince you exactly how this the belief propagation algorithm works in that case, in the non-tree case. But it's possible to define sort of the message update rules, how each node takes in inputs and then outputs something on its outgoing leg according to a specific rule, and then you can just run this and hope for the best. If the graph is a tree, you're just doing this contraction, and then of course it will exactly give you px2. Okay. Good. So now we want to use this in error correcting coding, or coding for noisy channels. And so just to remind you of the general setup, that's over here on the left. We have our message that we want to send. We encode it somehow. We're going to have many noisy channels. Here it's called W, that the message goes through. And so we have some encoding circuit or function or what have you, that transforms the message into the, so at this point in the circuit or in the diagram, you have the code word of the error correcting code, and then there's the noisy channel, and the outputs of the noisy channel are fed into the decoder, which is supposed to produce the decoded message. This is the standard thing. And in this case, what we're going to specialize to are the scenario where we have a uniformly random message. So yeah, the messages are chosen uniformly at random. We're only going to consider linear code, and we're going to try to decode bitwise. Okay, so what that means is we're going to try to determine from all of the outputs here, or here, we'll try to determine what is this value, and then what is this value, and so on. And from that, hopefully we'll reconstruct a valid code word, and then we'll know what the message was. All right, that's the general setting. And let's see, next. Okay, so here's actually our original, like the same factorization example now, where the function f and g are just sum modulo 2 has to equal 0. And so so the function, I mean, the value is 0 if the sum of the legs, now everything is binary, is 0 mod 2, and if sorry, it's not, it's 1 if the sum is 0 mod 2 and it's 0 otherwise. Okay, so it enforces the parity checks of this particular error correcting code here, whose parity check matrix is this H. It's a pretty stupid error correcting code, but it's good for illustrating how this algorithm works. Okay, so this Forney style factor graph or tensor network or what have you now describes what you would see at the output of this whole scheme for a uniformly random message, because we're going to sum over these guys here. So it's effectively going to just be uniformly at random. It's as if you just pick the messages uniformly at random. And then this part of the diagram enforces the constraints that you have to have a valid code word. Okay, so it looks just like this. This isn't the encoding circuit per se. It just enforces that the random variables here are always valid code words. Of course, we can, as Michel alluded to, you could try to look at, well, what's the tensor network that describes the mapping from the input code word to the output of the channel, and that you can get that by just inserting these half edges and equality nodes everywhere on the appropriate legs. So here we just had, this is the X4 input, so we can just sort of pull it out with this equality node. And then, okay. Of course, the decoder isn't seeing a random variable, it just sees some particular value, right? Y1, Y2, Y3, or Y4. And so I indicate that with this smaller box here, and it just means this tensor is 0 unless Y1, unless this sort of random variable is the value Y1. It's 0 if it's not the value Y1, and it's 1 otherwise. So this is the task of the decoder, essentially, phrased in terms of this tensor network, this factor graph. So it would like to know what's relevant is the probability distribution over these things, subject to the fact that the X1, X2, X3, X4, subject to the fact that they make up a valid code word. And now our strategy is to decode bitwise, so we can employ the belief propagation algorithm to do that. We just need to find the marginal probability distribution for X1, figure out what the largest, the most likely one is, set the X1 to that value, then do the same for X2. Actually, we can do these things in parallel in the classical case. Okay, so here's what it looks like now. We just want to find the estimate. We just want to decode X2. And we are given, of course, the channel output. And so this is the factor graph. The contraction rules are basically what I said. We would just, contract this part together. Maybe you want to think of it as first contract this part, or these parts, and then we would do the red one. We can also do, I guess, this one together. Or we should split this equality node actually, so that we can take everything in pairs, but we can always do that. And so this will be the belief propagation algorithm. This is exactly what is done in these classical error correcting codes, especially for low density parity check codes. Terribly relevant for the talk here, but in fact, these are used now in modern coding schemes. Okay, so this is how everything works in the classical domain. Next, okay. Let me take a break from that line of thought and tell you other uses of belief propagation that are not really related to this talk. It's important because belief propagation has a lot of different uses, and I want to make sure that you know where this stuff sits in that whole world. The oldest one, the original one in some sense, is to approximate free energy of a spin system. And the certain approximation is called the beta-Peierls approximation. It's funny that the acronym fits, even though the formulation by Beta and Peierls has nothing to do with tensor networks, factor graph, any of that stuff. They had a specific idea of how to approximate the free energy of a spin system that has certain interactions. Basically, try to construct a free energy just out of the local interactions. And it turns out that the belief propagation algorithm is a means to compute the optimizer within that variational class. That wasn't realized until 2000s or so. The Beta-Peierls approximation goes back much farther than that, of course. You can do it, obviously, for classical spin systems, also quantum spin systems. More recently, there was methods of or ideas of how to try to make a version that would work on quantum spin systems. So that's one big topic of belief propagation, and one way to see it, which is also very nice sometimes to look at it through this lens. Another one in the quantum domain, now these are more quantum things, these second 2 points. Just like we wanted to marginalize probability distributions, we could try to marginalize density operators. And okay, so you can try to do that. That's a sense of quantum belief propagation. We could also try to decode quantum stabilizer codes using belief propagation, something that certainly happens and people try numerically, right? This is really classical belief propagation for a quantum problem. So all of these three different things are very distinct from what I'm talking about here. Here's some of the references for these different topics. So this is actually a paper where I think that pointed out that this beta-Peierls approximation is actually found, the variational optimizer is found by the belief propagation algorithm. And the other ones here have to do with all of these topics, actually. Quantum approximations to free energy, marginalization of density matrices, and actually none of these deal with decoding quantum stabilizer codes. That's a pretty standard thing that people look at, but it's not listed here. Okay, so good. So now returning to the outline, the next part is to tell you about this quantum algorithm. So to estimate single bits from quantum outputs. Oh, it doesn't want to go to the next slide. Okay. So now we're in the same setting as we were before, essentially. I mean, the idea for, what kind of, can we make a quantum version of belief propagation? Or is there some quantum sense of graphical models? Just pick a classical problem and, translate it turn it into a quantum problem and try to solve that one and see if there's any relation. Pick a problem that you would solve with these graphical model techniques and see if you can port it to the quantum case. So here's the simplest version of that. And it's the same setup on these first two steps. We still have a classical message. So we're still trying to transmit classical information. So we have a classical encoder. Now, instead, we have the noisy channels are channels that have quantum output. So this is like the cheapest extension of the problem, right? Instead of classical output here, we have quantum output. So now we need a quantum decoder, and we want it to output a guess of the actual message that went in up here at the top. So the only thing, these things are all the same. We're going to pick our messages uniformly at random. We're going to use linear code. You saw in the previous picture how that fits very nicely with the factor graph. We just put in these parity check nodes, essentially, to enforce that we have a linear code, that we have a code word here. And the only thing we change is, whoops, this channel, we change it to a CQ channel. We still want to try to decode bitwise. But now our quantum decoder is going to have to be some circuit to implement a measurement, because it's got to take the output here and then output some classical value. So it's a measurement. It takes quantum input and spits out a classical value. It must be a measurement. This is what really, this is the big distinction to the classical case. So in the classical case, we use the marginalization. The fact that belief propagation is designed and implements marginalization of the probability distribution, we just use that to do the decoding. If we wanted to, if we take the analogy too seriously, and we'd say, okay, well, now we're in this problem, let's marginalize the density operator. And then we'll just look at that and try to get the result from that. But of course, that doesn't make any sense, because what the decoder has as input is not the density operator, it has the quantum state. It has to do something with the quantum state. It can't. So that's the big distinction between some of the work that came before. In the classical domain, we can use the fact that we're going to just marginalize the probability distribution in order to do the decoding. We cannot do that in the quantum case because the input is different, right? The input is now quantum. Okay. So as I said, we'll pick the simplest possible extension. So we already have a CQ state, and we'll pick a specific one here. The simplest possible CQ state, I would say, is a channel that has binary input, and the output is a pure state. And let's say it's symmetric. So it's one of two pure states called phi x. And yeah, I mean, any two pure states are symmetric essentially. So like you can flip one into the other with a unitary. Okay, so what we need to do, as I was just saying, is construct a measurement to estimate x2. Let's say we want to estimate x2 from these quantum outputs. Now here in the factor graph, I wrote it with 2 legs. And that's because this factor graph should, like tensor network, well, maybe that was a bad thing to say. This factor graph should represent the density matrix, basically, of the output. So in the classical case, we had the graph where there was just single edge here, and there was y1, y2, y3, y4 that represented the probability distribution at the output of the channel, of the noisy channels, given that you have a randomly chosen code word. This one is supposed to represent the density operator at the output. And so because it's a matrix, it has 2 legs to it, essentially. So that's why there are 2 here. I mean, a lot of tensor network use in the quantum case, of course, is to describe pure states. And we do have pure states here, but we're going to need to describe mixed states in general. So we need these 2 legs. So in the tensor network usage in the quantum world, most of the time you're trying to describe pure states. So you would just have 1 leg per system, but that's not going to be enough here. Okay. Now, I've already said the tensor network contraction is not enough, of course, because we do not have, we can't put a quantum system into this graph. That doesn't really make sense. Okay. So now before I tell you the algorithm, let me just tell you how we'll model or describe the outputs of this CQ channel, just to make it easier to present the algorithm. Of course, it's 2 pure states, so describe it how you want. But in terms of the block sphere, I think it's nice to, you can always arrange the 2 pure states symmetrically along the z-axis if you want. You can just think of it as a qubit. There's only 2 pure states. And then for us here, a nice parameterization will just be the height of this z component of the block vector, and of course, whether it's pointing along the x direction or against it. That would be the bit value 0 and 1. Okay, so the block vector is going to be this thing for the output pure state. So you can see the value of z is what we need, and also x. X is the input to that channel, just like we've been using so far in the factor graph. Okay, so this is the parameterization you don't have to worry about it, you don't have to follow this exactly, but it would just be easier to write the rules for the belief propagation, what's going to happen next in terms of this z parameter. Okay, so here is the algorithm. Now, I will try to do this more in the CS sense for this audience. That is, I will just tell you the algorithm, and then we will describe why it's useful or interesting later. This goes against my usual style as coming from physics, but I also have had the experience that doesn't work very well either. So let me just tell you what the algorithm is and show you a quick example of it. And then I will tell you why it's interesting, or what it's trying to do exactly. Okay, so first of all, here's the original setup for decoding X2. The nice thing of the factor graph, you don't have to be constantly labeling all these different edges. And also we have some simplification that we can make, because the sum modulo 2 of just 2 random variables, if that has to equal 0, then of course the 2 random variables are 2 binary random variables are equal. So we can just replace that with equality. This one, we can't do that, of course, because it has 3 legs. So let's do that. So this is the case we're interested in. We have these outputs here, and we want to somehow compute a guess as to this classical input. So, okay, here's the algorithm. And so the idea of it is described in the first 2 parts. Let me say that first. So we're going to traverse the tree. Now, these graphs are always going to be trees for us. From these W leaves down to the root, right? So we're always going to have this tree structure for every bit that we pick. And we're going to kind of traverse this tree from the leaves to the root. As we're going to create a quantum circuit from this. And the way we're going to do that is on the graph side of things, not on the circuit side, we're going to associate a qubit and this Z parameter to each node. Okay, so all these different things. So this one is clear. These are just the channel. So the qubit and the parameter for this node here is of course just this qubit and the parameter that goes with this channel. Okay, so for the leaves, it's clear. Then we start working our way back towards the root, and we're going to update these parameters and fix which qubits we're talking about as we go. Okay, so what we're going to do is at the equality nodes, we are going to apply a certain unitary. So, okay, I slightly lied there about just give you the algorithm. I'm not going to say exactly what the unitary is until later when it's obvious what it should be. But there's going to be some specific unitary that we apply to the two qubits that you know, we're looking at this node, this equality node here. It has, from the point of view of the direction towards the root, it has two children or two leaves or whatever. And those have, each one has a qubit associated with it. So for these qubits, we're going to apply this specific unitary, which depends on the parameters that go with these two channels, Z1 and Z2. They could be different. I mean, in this case, they're the same because I wrote W for all of them, but in general, they are different. So we have to apply a specific unitary to this. Then actually, after we do this unitary, we're going to discard the second qubit and then set the parameter for this node to be the product of the two Z values. So the qubit that's associated to this one is the one that we keep after we do this unitary, and the parameter that goes with it is this thing. So something different is happening at the plus nodes, or these are actually called the check nodes because they enforce the parity checks. To the two qubits, we're going to apply a C0. We're going to measure the second qubit of the target and get some result. We're going to measure it on a standard basis. We get some result, call it K. And then we're going to discard that qubit that we measured. So this node here is going to take the control qubit in the end of the C0. And then the parameter that we're interested in here depends on the measurement value. So we're going to reset, first we're going to kind of reset the Z2 parameter of what's coming in. Let me see here. What's coming in here, we had Z1, Z2. Then we're just going to reset this parameter value here to be, we're just going to flip it basically if the measurement result is 1. And then the parameter in the end that goes with this node is this kind of ugly thing. It's Z1 plus Z2 divided by 1 plus their product. Okay, we do this for every node. We go all the way through the graph. We're applying unitaries and other things. We're doing measurements on the qubits as we go, on the actual qubits. Then we're going to get down to the root. And there's going to be one qubit left. And at the very end, we just measure this one in the X basis. So remember, our parameterization is zero state is aligned with the X-axis, more in the direction of the X-axis, and the 1, phi 1 is against it. So if you wanted to measure just the channel output here to determine what the bit value is, the best measurement to make is just to measure along the X-axis. Okay. So let me give an example of this. So here's the circuit that is constructed when we do this. So over here, of course, the graph is the same. So here's the unitary that we need to apply. We're going to apply it to the first two qubits. We discarded the, we discard the second qubit. We can, which one is first and which one is second, we can always pick. Since we want to decode X2, it's nice to leave the last qubit as the second qubit number 2, let's call it. So in this unitary here, which goes with this node, the qubit number 1 is the second qubit. So we discard it, that's why the line stops. Then it continues on. Here we're doing the check node steps that we're supposed to do. We do the C0 gate, we do a measurement. Depending on the measurement result, then that's going to be useful later on this variable node. So the equality node is sometimes called the variable node. So here's the unitary that goes with this one. So step 1 is this one, step 2 is this one, and step 3 is that one. the one at the root, and then finally we have the last qubit and we make the X measurement. So here's the output. So exactly opposite, I mean, the circuit diagram is exactly opposite to this kind of factor graph tensor network where, oh, sorry. Here, of course, the two lines represent a density matrix. Here they represent classical information. Single lines here are classical information. Single line here is a qubit. Okay, so that's annoying, but I think we're used to this picture at least. Okay, and these are just the rules. I just wrote them here again, so you can see it all in one slide. So this is how we translate. We traverse this tree and create this circuit. Okay, and this is going to do something useful for us. And in fact, what it does is it implements the bitwise optimal measurement. So we look at this graph now, alluding back to Michael's question again, we could think of it as a classical channel that takes this input and just spits out these quantum systems down here, right? And it has 1-bit input and it has 4-qubit output, but never mind how many qubits it has at the output. There is some optimal measurement to decide what the bit value is, the Hellstrom measurement for this case. And the algorithm BPQM is actually implementing that Hellstrom measurement. How can I be so sure? Well, you just have to decompose. You can see what the algorithm is doing is sort of simplifying this factor graph in a recursive way. And at every step, it's sort of obvious that, one step is very obvious and the other step is not so hard to see. It's going to do the correct thing. So let me tell you what that correct thing is. So just as we can think of this factor graph as representing the classical channel from this input here to these outputs, we can do that for every, I mean, once we have this as the root, then we can do that for every node in the graph. I mean, this is of course already a channel. This is the input, this is the output. And we could take this one. So we could just think about what is this channel here effectively that goes, oops. Okay, press this. Oh, I seem to have lost that. Okay, that's fine. So we were looking at this channel here, and it sort of has this as inputs, and these are the outputs. Well, what is it? Of course, this equality node just means the same value goes down here, so we get the same input to these two class CQ channels. And obviously at the output of this thing, we're going to get either the product of phi 0 and phi 0 prime, maybe the two channels have different parameters, the different z parameters, so there's a prime here, or we're going to get this one. It's a tensor product of two pure states. The only possible outputs here basically span 2 dimensions. And so what this unitary is that I didn't tell you, its exact form, it just repackages that state space. Now, I mean, nominally we have 2 qubits here, 2-qubit output, but there's only 1 qubit of information in there. It just repackages that as 1 qubit. Okay, so it's not really that important to know exactly what this unitary looks like. The only thing that really matters is it definitely depends on the parameters of these states, right? There's no sort of universal way of doing that because the states move around in this 2-dimensional subspace moves around in the 4 dimensions of the 2 qubits. Okay, so that's all that's happening at this stage. So we could imagine that, I mean, we just draw in the unitary here. I guess it depends on Z1, Z2. Okay, this is ugly, but, and it has 2 outputs. One of them, in fact, is going to be in the state 0. So we don't care about that one anymore. And now we can just replace this whole thing in our factor graph. I mean, we can draw a line around this whole part. And we've simplified the factor graph. We've simplified what the channel output, like what the decoder is going to see. We know that if we apply this unitary, we're going to have a state at the output, which is just given by this new factor graph. And it's going to be, as we just saw, it's going to be a new channel, effectively. It's just got it's a new channel of exactly the same kind. It has classical input, binary classical input, and outputs one of 2 pure states. So we can just compact the whole factor graph, and now everything is a lot simpler. And because of that, we're definitely not losing any information when we want to do the Hellstrom measurement, right? everything is still there as it was. We could undo it if we wanted. The check node, the plus node, is not so straightforward, but it turns out that after you apply C naught, and so at this point here, maybe sort of graphically write C naught in here. If we do the C naught, then the state at the output of this effective channel is a CQ state where, so that's written here. This is very ugly here, but it's going to be on the second qubit. The target is going to be in one of two classical values, and then there's going to be these pure states again on the first qubit, and the particular angles and so on, or this z parameter. We'll sometimes also use the angle to the z axis, of course. The parameters depend on this value of k. And there's some probability distribution for getting particular outcome k, but actually we don't really care about that. So the point is the C naught will just transform it into a CQ state where we have the this pure state again, and it's sort of heralded. So the specific pure state channel that we have is given to us by the classical value. Okay, so this allows us to recursively simplify this factor graph in this way. And of course, therefore, essentially, this is why we're doing the Hellstrom measurement, because we're going to get down to just one qubit in the end. And we know that it's always going to be this two pure states at every stage in the simplification. And once we have just one qubit left, we know that the optimal measurement is the X measurement. So that's the argument. Okay, good. So that was actually the main part of the talk. The rest is a little bit more high level. So now if we want to decode, I mean, that's all well and good to decode a single bit, but we need to decode every bit, or at least enough of them to reconstruct the code word. And here's where things get a little bit trickier, but the basic idea that we're going to do is we'll just run the decoders sequentially. We cannot run them in parallel like we could in the classical case, but we can just run one after the other. Why would we do that? Well, if the bitwise error probability is low, so like if each one succeeds with high probability, then we can use the union bound to say that the whole code word is decoded correctly. And this will work for certain capacity achieving codes. In particular, polar codes is a specific kind of error correcting code that can achieve capacity in the classical case. This is how the argument goes. It decodes sequentially also, and it's a union bound type argument. So for instance, in the running example that we have, we decode x2. That's this graph that we've seen many times. And we don't need to decode x1 once we've decoded x2, or at any time if we also have x2, because of course they're equal. So we'll decode x3 instead. This is the graph that goes with x3, right? We just rip out this equality node, and now this one is the root. So everything looks different. Great, so this is the basic idea when we want to decode the entire thing. And there's a few huge problems, actually. First of all, the BPQM algorithm is making these intermediate measurements all over the place. Every time there's a check node, this plus node, it's going to measure one of the qubits. This is not good because it's, you know, when you after you've done the first measure, decoded the first bit that you want to do, well, the second bit you can try to decode it, but at that point in the circuit, the output has nothing to do with decoding, like the factor graph that goes with decoding the second bit. So actually, this sounds like a dumb idea. But what you could do is run everything coherently. So instead of doing this circuit here, I compacted it a bit. So like these two steps are running in parallel, and then here's the measurement, and it just controls this. Because the angles or the z parameter of the channel depends on the measurement result, we have to feed that information into this this unitary here, which goes with the check node. Sorry, it goes with the variable node at the root, the equality node. And of course, this part is the same. We'll just transform that into a quantum kind of control. Now, I should say this is not quite correct, because what we need is a kind of universal control, because what we need to do at this stage, it's not like controlled not, where, you know, in one case we do nothing. We need to do a different specific unitary for each possible value of the measurement result here. So this circle here should be one of these half open, closed, whatever, half filled circles, so that it looks like something non-trivial is happening for every possible value of this wire. Okay, then what we can do is then run the circuit up to this point. We make our measurement to determine the bit, and then we can just run it backwards and invert it. Now, if the measurement succeeds with high probability, this won't damage the state very much. The measurement won't, effectively, the measurement didn't occur. So then we can just unwind this or rewind the circuit. And then when we come to do the next one, we know that we're in a good position to decode because we have the same state that's described by the factor graph. Okay, there's a problem with that. And that is every time there's a check node, there's this control, and we have to do something different depending on the two values that go with that. And these check nodes are, there's not just one of them. So it's actually an exponential overhead from these controls. And what we can do is go back to the original description of the algorithm in terms of, we associate to every node a qubit and this z parameter, and we were traversing the graph. We were sort of passing messages through the graph, and we'll just quantize this z register. We'll just make it a quantum system instead, and then we can control everything off of that. So every time there's a measurement, we'll just update the value of the z parameter in this actual quantum register. And then once we've used it, we can uncompute it. The problem with that, of course, is you would need infinite dimensions to store this, this value of z, which is somewhere between 1 and -1. But we can discretize it to finite precision. And of course, this is sort of standard thing that fortunately works here as well, that for target error, the size of the number of qubits you need to represent that to decent error is only logarithmic in 1 over the error that you want to make. So that's good. And what's nice about this version, this is the stuff that's come up more recently. So the original paper that I wrote on this basically doesn't notice that, that there's going to be an exponential overhead. And so we recently realized that we can fix this problem in this way. And what's really great about it is that now all the messages that are passed are quantum. You can really see the algorithm is doing message passing, just like in the classical case. And everything is quantum. Okay, so just a couple more comments here about this. Last year, there was a paper, I think it should be published soon, but on this BPQM algorithm, a sort of version 2 of it that makes a couple of improvements by Rangaswamy and et al. I won't try to say all the names. It's from the group of Henry Pfister at Duke and Saikat Guha in Arizona. And what they realize is that, well, at this stage in the circuit, you make this measurement, but at this stage right here, you know what the z parameter is of the state. So after you make the measurement, you should try to reset the qubit into one of those states. I mean, the measurement is going to project it onto the z-axis, right, this qubit. But it started off sort of somewhere either this way or this way, and then the measurement produces this. And you should just fold it back up. And you should also use the updated factor graph in the subsequent bits. So I really wanted to show this to show that BPQM version 1 is not doing that. I showed you the factor graphs for decoding X2 and X3. And you notice that we were going to decode sequentially, but we didn't use the fact in decoding X3 that we had already decoded X2. And of course, that will make things a little bit easier. And just to show, in their case, they were looking at a certain 5-qubit code very numerically. And this is the graph that goes with it. This is in the original style of this factor graph that I mentioned. So now the variables are these circles. And what we have as nodes in this Forney style are the square ones. And after you've decoded the first, after you've decoded X1, now you know this value. Of course, the factor graph splits into simple parts. So that's the reason I wanted to show this. It's much simpler in this sense. What was crazy about it is they looked at this numerically, and it appears to implement, if you do things in this way, their version 2, it appears to implement the block optimal decoding measurement. So we want, here in this decoding task, we were trying to determine the code word by decoding each bit separately. And we saw that I tried to argue that each one of those individual bit measurements is optimal for the task of estimating that bit. But of course, the task in the background, the task that we actually want to solve is to decode the entire input. And that's the block decoding question. And this version seems to to implement the block optimal decoder. And we can see that also in the, so in the original paper, there was a certain 4-qubit code that's it's essentially the same one as I was showing you in these examples. And you can see that it's also true there, that this BPQM version 2 implements the block optimal measurement in that case, not just this 5-qubit case. So this is very interesting to see if it's true for other codes as well. Okay, so now time is running short. I will skip over the applications or just mention them very briefly and then leave you with the summary and open questions. The applications are that you can use this for to build efficient decoders for high rate or even capacity achieving codes. And there's 2 examples that come to mind right away that work out right away. I mean, the classical communication, just the setting we were talking about, the code we would look at is a polar code. So all of the stuff that I presented was based on using, like having tree graphs. And its main use in the classical case is to have, to decode low density parity check codes, for which you can make some assumptions about the tree-like structure. They usually are not trees, but they're close enough. But another case is polar codes, which also have a certain tree-like structure, but it's not the same tree structure as we were looking at. So we were looking at kind of, here's the code word, the input to the channel. This is the encoding circuit of the polar code essentially. And what's going to happen is also for Reed-Muller codes, you're going to set some of these values to be 0. And then the rest, the free values are the inputs. You know, that's where you put the messages in. And on this, in the graph that comes from this encoding circuit, you have a tree-like structure, and that's how it's decoded. And in fact, it uses the same equality and or equals and plus nodes like in the way that the decoder works. I can't tell you that all the details now. That would be another very long talk. But the basic point is that we can still use this decoder, the BPQM decoder, for this problem. So we could think about the pure loss bosonic channel. We want to send classical information using photons. We have very low power. We're just going to use coherent states. Let's just use 2 possible coherent states. This is called BPSK, the binary phase shift keying or something like that. Anyway, it's a specific encoding for this channel, the pure loss bosonic channel. So you would encode into 2 different coherent states. They're not orthogonal. It's exactly this pure state channel we were talking about. If the receiver just gets a lossy version of that, it's also still a pure state. And so we have exactly the setting. So we can use the BPQM algorithm to give an efficient decoder that can achieve at least the capacity of this kind of encoding scheme. Okay. With a lot more work, I think you could get the actual capacity of the pure loss bosonic channel for classical communication using polar codes, but it's a much more complicated argument. So this is a specific encoding of classical information into quantum systems that at least we can achieve the capacity of that. And the second one is actually you can use this for quantum communication. You might have been thinking the whole time, like, this is nice, but like it's half classical and I don't like those kinds of problems. But the great thing is that the quantum version of polar codes just uses the classical input polar codes as subroutine. And so if you can construct polar codes for these classical input problems, then you can combine them to create decoders for codes and decoders for quantum polar codes. And in particular, the amplitude damping channel works out very nicely because the 2 subroutines that you need to consider, one of them is a very specific classical channel that's well understood, but it's purely classical. So we can just use that result. And the second one, the second part is actually this pure state output channel. It's sort of heralded again. There's an extra bit that tells you what the angle or what the Z parameter of that channel is, but it's exactly the setting that we just talked about. And so in this case, the BPQM algorithm will give an efficient decoder that actually achieves capacity for this scheme, because the polar codes can achieve capacity, and now we know how to do the decoding. All right, so now we've come to the end, to the summary and open questions. And so looking back, I mean, the main thing I wanted to present was actually just to get you interested in this question of quantum graphical models and algorithms in this domain, and to present this BPQM as an instance of that, and maybe something that can be extended in different directions and so on, or just use it as an idea to do something completely different. That would be fantastic. I understand not everyone is interested in error correction. So that was, of course, the main content that I presented today. But even in this domain, there are a lot of obvious questions that come out of this that also relate to this general problem of the general setting of graphical models. Let me start here at the bottom, maybe in that sense. So can we do this algorithm when the factor graph has loops? So I alluded to the fact that you can do classical belief propagation when there's loops in the graph. It's not a tree. And this is a huge question because you can still run the classical one and just hope for the best. And often it's good enough. How do we actually apply this to low density parity check codes? It would be great if we could start to build decoders for quantum, or maybe half classical quantum low density parity check codes using this. But if we can't do this, the loop case, we're kind of stuck because usually these have at least some loops. What about mixed state? We had this very specific example here of this pure state output channel, and that's the reason the algorithm works is very dependent on the fact that we only have these pure states at the output. So we need some much better understanding of what's going on in order to understand the mixed state case. And then the very interesting question that came up in this research recently is the blockwise optimality of at least this version 2 of this algorithm, which is something very interesting to study and see how far that goes. So with my student, Christophe, we were making some progress on these things, but we're not to the point where I can tell you I don't have anything to present yet, which might not turn out to be wrong. But I think there's quite a lot of hope for some of these questions here. The mixed state, I don't know about. But these are the general open questions from this topic, and of course, the general setting of graphical models. Okay, I've talked for a long time, and now I will stop and be happy to answer your questions.